Hey guys, welcome to HaskellRank episode 5. Um, so far we've done two easy and two medium hacker rank problems, and for episode 5, I had a very specific goal in mind, and the goal was to showcase and make use of custom types in Haskell. Now, there are obviously a bunch of ways we can create types, and then shortly we'll see that. However, when I was evaluating different problems from HackerRank, I noticed that the majority of the problems over there have a very sort of like an algorithmic, you know, sort of approach to their problem solutions, which doesn't allow me to utilize uh, Haskell custom data types very easily. So for this episode, then I decided that instead of HackerRank, we'll look at maybe some other existing programming website. I ended up choosing Advent of Code. And now, for folks who are not aware of Advent of Code, I would strongly recommend you guys go and check out adventofcode.com. They were pretty fascinating uh, structure right there. Their competition essentially runs from December 1st to December 25 every year, and they typically have some kind of a Christmas theme based storyline behind all of the problem statements. First thing first, we have our boilerplate. I already have that. So let's start with the problem statement. Handheld halting. Your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, your puzzle input of the device. You should be able to fix it, but first you will need to be able to run the code in isolation. Okay. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an operation, which will be either ACC, jump, or nope, and an argument, signed number like +4 or -20. Now, ACC increases or decreases a single global value called accumulator um, by the value given in the argument. Essentially, this idea is similar to the notion of a register. Now, most processors have a bunch of registers, which are often used for this kind of purpose, where we store values in them, and we can retrieve them, and we can manipulate them. And these registers exist on board, and hence obviously are uh, in terms of the performance and everything, they're pretty fast to use. So for example, ACC plus 7 would increase the accumulator by 7. The accumulator starts at 0. Okay. After an ACC instruction, the instruction immediately below it is executed next. Okay. The JMP jumps to a new instruction relative to itself. Okay. The next instruction to execute is found using the argument as an offset from the jump instruction. For example, jump +2 would skip the next instruction. Jump +1 would continue to the instruction immediately below it, and jump -20 would cause the instruction 20 lines above to be executed next. Nope stands for no operation, it does nothing. The instruction immediately below it is executed next. Okay. For example, consider the following program. Okay, so I'm going to copy this and we'll use this as our test input, right? Okay, it looks simple enough. So these instructions are visited in this order. So we execute the first instruction, which is a nope instruction. So we move to the next instruction, which is an ACC +1. So we increment the global accumulator register value and then move to the next statement. The next statement is a jump statement saying +4. So after jump +4, we would then move 1, 2, 3, 4 lines down to accumulator +1. And then that increments it by 1, so it'll become 2 now. And then the next statement says, okay, no, you jump 4 steps back, which would have us get back to accumulator 3 plus 3, which means 2 plus 3 becomes 5. The next statement says again jump -3, so we 1, 2, 3, we jump back to accumulator +1 statement. So we've come back to this statement again, and obviously this will continue, I think, a bunch of times. So I mean, and this is exactly how this is by design. The jump operation, typically, if you look at least some assembly code, you will see that it's actually what is used to loop through a certain set of operations. This is an infinite loop. Makes sense. With this sequence of jumps, the program will run forever. The moment the programmer tries to run any instruction a second time, you know it will never terminate. Good to know. Immediately before the program would run an instruction a second time, the value in the accumulator is 5. It was 5, yes. Okay. Now run your copy of the boot code. Immediately before any instruction is executed a second time, what value is in the accumulator? Okay. So that's the problem statement. Okay. Now let's try to model the different parts of the problem statement, right? So the first basic thing we have is we have an argument. And so what I'm now going to do is I'm going to, since it says clearly that an argument is a signed number, what I'm going to do is just basically type alias argument to integer. Now, for those who don't know what type aliasing is, it's basically a very simple way to say that to basically create a custom name for an existing type. So it's just a custom name underlying and underneath. It works and behaves exactly like the fundamental data type you're aliasing. You get all the functionality and all the properties that come from the Haskell standard library from the int data type in this case, and you get everything out of the box. And so you don't have to do any, or at least much of any custom handling per se, right? Like for instance, since it's an int and it's we are type aliasing an int, we can utilize the show function to show it because Haskell already knows how to show integers. We can use the read function to parse the argument because that knows how to read integers, so on and so forth. And whatever properties and behavior that the int data type already has would automatically be available to us because we're just aliasing. And so from a logical standpoint, the value in doing something like this, where we are aliasing an existing type and essentially giving it a separate name, is more to do with basically it adds more value to your to the domain where your problem exists, right? So it makes it easier for you to interpret and read and understand what something specific should be representing based on your problem domain, right? So argument is something very specific. However, of course, an integer is a fundamental data type, and you can have anything be an integer, right? But an argument is something very specific, especially when it comes to the instruction. It's something very specific. So doing a type alias gives us the ability to logically, have a separate, unique place for it in our type system. So this is the first kind of type. Then we have an operation, and an operation we see is something that it says that it can either be an ACC, jump, or a nope. So let's now use the data constructor to create the operation type. And just as we see, what I will do is I will mimic exactly how the problem statement describes. So the operator, or rather the operation, can either be ACC or jump or nope. Okay, yeah, so let's dissect this. So now when we use the data constructor, essentially that allows us to create a custom type. And in this case, it's essentially a kind of an enum, right? So we say that the type operation is represented by either an ACC, JMP, or a nope, right? Now from Haskell's lingo perspective, technically these are value constructors. However, in this specific case, we are not, they're just raw constants, if you will, right? Um, they just represent something abstract, and they don't actually hold any data per se. So we won't actually be doing any kind of value construction per se, but we will definitely utilize them in our pattern matching, because we can pattern match based on the value constructors, right? And that I think we will probably heavily use, because then we can conditionally pattern match and do different operations based on the type, or rather, yeah, based on which specific operation we are going to be handling. Maybe at this point, I think maybe it might yeah, it might work better to show you what these look like, right? So once we get to GHCI, now in Haskell, what you can do, if there was if we needed to do, was you can say, okay, what is the kind of operation, and what kind gives you essentially is it basically describes what kind of a type this is. And without going into a lot of complexity and detail, I, I I think I'll probably tell you the fact that, the type system in Haskell is extremely rich, and you can build fairly complex types, which are which may not necessarily be just raw types such as this, right? So this, in this case, when you look at the kind value, it says, operation is star, which means it's just it could be anything, right? But it's just a single entity. But just to show, maybe, yeah, if you look at what is the kind of maybe, you'll see that for maybe it says, maybe is a type which maps from star to a star, which means you need at least two or at least one argument with maybe to make a concrete type, right? Maybe by itself is not a type. It's something in Haskell known as a type constructor, because only when you combine maybe with something else, such as an int. Now if we look at the kind of maybe, we see that it's this, but when you combine maybe with some other fundamental type, now we've already applied the type int to maybe. And as you can see, I mean, like in Haskell, this is essentially uh, it's very similar to a function, which it says that, okay, it's a function that maps that takes one argument and returns another, right? So when we apply int to maybe, then we see that we finally get a raw type, which is just a type by itself, right? However, maybe is not a type, it's a type constructor. It's only when you combine it with another entity, that's when you form an actual concrete type. And okay. So now that we have this, I think that's good. We have an argument, we have an operation. Now let's create the instruction type then. So instruction type, I would make it something like this. So I say data instruction. So we create a type with the name instruction. And we already know that an instruction consists of an operation and an argument. So we literally just say that. So instruction, operation, and argument. And this is all you need to create the instruction type. Now, this can be confusing for uh, for uh, for beginners who are learning Haskell, and definitely this is something that always confused me, because initially I mean that's also partly because I never bothered trying to actually dig deeper. I always assumed wrongly that this instruction you see on the left hand side is the same as the instruction on the right hand side, but in reality they are completely different. What you see on the left of the equal operator, this is the type. However, what you see on the right hand side of your equals equation is actually a value constructor. Like I explained, ACC, jump, nope here are essentially value constructors. However, they are very simplistic value constructors because they don't actually compose with other types to form something. So they are also values in themselves. However, for instruction, we see that we have a value constructor which, when combined with an operation and an argument, finally then will it produce an instruction type, right? So let's see how what that looks like. So when we look at the type of instruction, and when we say this, Haskell already knows. Haskell already knows that we obviously cannot look at the type of instruction, the type. We can only look at the type of instruction, the value constructor. And so that's exactly what Haskell will show you. It'll show you that instruction, the value constructor, is essentially a function that receives an operation and an argument, and and uses that in some way to finally produce a value of type instruction. So to showcase, yeah, right. I think this looks decent, and I think you guys should be able to understand it now. So now that we have an instruction, an operation, and an argument, now let's go to the next step. The next step for us should be essentially to now to actually parse the input data, right? Let's parse the input data and at least be able to get a list of instructions, right? So we have just a list of all the instructions as string. We will eventually pass them to actually be of instruction type, right? And let's see how we can do that. I think the first thing I'll probably do is I'll probably try to write the logic for passing those individual, because an instruction is composed of an operation and an argument. So obviously it makes sense that I'll first write my uh, logic to pass an operation and an argument, and then finally I can easily write a parser for passing the entire instruction string. So let's try that. So let's do argument first, because obviously that's much simpler. So that would look something like this. So pass argument, and that will take a string, and then that will return an argument type. which behind the scenes is integer, but yeah. So I will say, okay, parse argument. Okay, so okay. So now let's see what this should be, right? So now that we have it, now let's try to think a little bit about how to actually do the parsing. Now we've been passing numbers uh, all um, throughout our problems so far, right? However, the numbers here are slightly different, and let's see how they behave. How the parser behaves when try to parse this. Now the parser we use obviously for parsing numbers is read, right? I mean, yeah, that's slightly misleading maybe, or at least that's definitely a partial information. Now read is something that we can use to parse literally anything. The type of read, if you look at, is that it receives a string as an argument and then produces something of a type A, where A can be anything, as long as it conforms to the read interface or the read type class, right? And I'll not at the moment I'll not get into describing what a type class is, but like I said, the idea of an interface is probably something most folks are slightly more familiar with, coming from backgrounds like Java and stuff. So it's something very similar to that, and so we can just pass a string which says, let's say, -4, and by this default obviously read would complain because read doesn't know what data type we want it to be passed into. So we'll manually say, okay, now I want an integer, and that works already, that works out of the box. So for read -4, and when we say that, okay, yeah, this should be an int, it already says, great, yeah, that's -4. Now let's look at maybe +1. So when we say read +1 of, and then converts that to an int, unfortunately read fails to parse this. Now I don't know exactly why, but my gut feeling is it's probably because of the fact that when it's trying to parse, it sees when it sees the plus sign, or the plus character rather, it probably thinks that that plus represents maybe the plus function or something different than a number, a digit. And so for that reason, then it says, no, I cannot pass plus into a number. That's what I believe is happening. So now what we would then have to do is we would have to figure out a way such that we would probably be ignoring the plus sign, right? And that works. So what we'll do is, if there is a plus sign, we will ignore it. Otherwise we just parse it using read. That's essentially what I want to do. And so for that we can do a very simple pattern match. So we can say parse argument +:ns, which means if the first character is plus and the rest of it is represented by ns, then uh, that should just basically read the rest of the argument, and that should be the output argument value. And whereas for maybe anything else, it should just be read, right? And this is fairly straightforward. So I think this, yeah, this should already be able to pass an argument. Let's reload, and let's now look at what pass argument of +1 is. That's 1. And maybe what pass argument of -1 is, and that's -1. So we have that. Let's look at parsing an operation, right? So, and that should again receive a string and finally produce a value of type operation. And I think, yeah, this is fairly straightforward again. So if we have the string acc, it'll be acc. If we have the string jump, we have jump, and it might actually result in bugs. So for that reason, let me simplify it and let's just use this. So now this is not an exhaustive pattern matching. However, because we know our input is guaranteed to have only either of these, we are still okay. We will never run into a situation where the pattern matching we've defined would ever fail. And as long as it doesn't fail, Haskell will still be all right. So now if we have that, we can say parsed operation ECC, and okay, this fails. Now, so the parsing itself did not fail. Obviously, the parsing is dead straightforward, so there's no reason for it to fail. What actually failed here is, if you read here, right, it says no instance for show operation arising from the use of print, which is to say that Haskell just doesn't know how to show this type, and that is something that we can very easily fix by saying that our type operation uh, derives from the show type class. And what this essentially does is basically applies the default implementation of the show function for the show type class, right, from the show type class. But this is sufficient enough for us, at least for the time being, right? And so now if we reload, now if we set parse operation is to C, we see that it's ACC, and so Haskell now does not complain because it knows how to show it. While we're at it, let's also do the same for our instruction data type. So now that we have an argument and an operation, let's pass an complete instruction. Okay, an instruction parser would receive a string and then finally produce an instruction. Okay, and so that, what will that look like? So let's say is is the instruction string, which would look something like no plus 0. And so obviously what we need to do is we need to break them down, right? We can use words for that. We can break them down into nope and plus 0, which is the argument, and then individually parse them. So let's first maybe just to remove the errors, I will say this, and then I will say, okay, where okay, yeah, we will get an error, sorry, we'll get an array, right? When we use words, we will essentially end up having two element array of strings, and so from that we use pattern matching to extract the operator string, and then we'll have the argument string, and that would just be words of is, right? And since we have that, now we can say, oh, our operation is parse operation of the operation string, and also our argument is parse argument of our string. And now we can simply say, oh, this should use the instruction value constructor, combine that with our operator and the argument to give us a type value of type instruction, right? This already passes. We can say pass instruction, let's say, oops, plus 0, and yeah, that works. So we are now successfully able to parse it, right? Okay, so this, I think we have everything we need in order to parse the input. The next thing we need to do is basically have a way for us to be able to actually execute these instructions. And the execution, there are a few things about the way that we need to execute that I need to think a little bit about. The one main thing is the fact that we have HCC as a sort of like this global register thing, right? So we need some kind of a place where we can hold the value for this register, right? Some kind of a state variable essentially, that would carry forward the value of the accumulator, and as we go and execute all the instructions one by one, so it will keep carrying the value. And the next thing is, because we have a jump statement, and then also the fact that it's relative, we obviously we need some kind of an think the technical term for this is an instruction pointer. So we need an instruction pointer which would essentially be a pointer to the current instruction we are evaluating, right? And as the program evaluation proceeds, the instruction pointer would typically navigate through these series of instructions, based on the code that we have, the the boot code, right? So I think the best way, yeah, I think the best way to do that would be wrap that into another type of its own. So the most logical type that comes to my mind would be to create an idea of a program that would hold all of this together. And as long as we have the right logic of actually executing these instructions, but we would be good, right? All we'll need to do is that we maintain all the state of the accumulator and the instruction pointer within this program type, and we should be good. And so that for that we will use uh, yet another different kind of type definition, which in Haskell's language is known as I think a record style definition. So what that looks like essentially is we can say, so we have ACC, let's say, and let's say that's an integer. Then we will have an instruction pointer, which is also an integer. And let's say we will have instructions, which would be an array of instructions, right? So this is a sort of slightly different new syntax we're seeing here. Let me break it down. So using the data, obviously we are creating a type called program. The type program can be created using the program value constructor, but then Haskell has the shorthand notation where we can, for a value constructor, using these curly braces, we can essentially say that this value constructor has a bunch of properties. Now, I think in theory, these could also be functions, but at least for our use case, all we need is essentially a set of properties, right? And so and so this is called as the record style of type that we are creating. Now there are a few things unique to this style. The first thing is that for all intents and purposes, this is very similar in concept to how you define, like, let's say a struct in C or even in Golang, right? Like, so you define a struct which is like a very low level custom data type that you can have, which can hold certain properties. So this essentially is Haskell's version of a very similar design. However, it does behave and it has certain unique properties and characteristics, which I'll show you in a little bit. Now, when we use this record style, essentially what Haskell does is it basically is a more what do you call convenient way of doing something like this, right? For instruction, all we did is we just say, okay, this is something that we can compose using an operation and an argument, right? There, if we really wanted to if I really wanted to showcase the record style, the similar analogous thing we could do there is the fact that we can create properties that hold the operation and an argument. But obviously I think that is probably not needed because it's just two values, right? And I think it should be good enough to do it that way. However, for a program, because we have a bunch of values and they're also slightly complex, like because the instructions essentially an array of instructions and things like that, I think this style kind of is probably a better representation for it. But the other nice thing about this, when you use this syntax to define your type, is all the properties that you define are essentially Haskell sees them and then creates, or rather generates, functions for those. So ACC, when we say okay, ACC is a property for the value constructor program, it ends up being a function, which is a very smart function. And so when we look at the type of ACC, you will notice ACC is essentially a function that receives a program as as an argument, and then from that program we would actually, in some ways extract that value that is represented by ACC, and we'll get that value as the output, right? Which means we can use this as a function as long as we have a program object. We can do something like ACC program, and then that will extract the value for the accumulator register for us from that program and give us the value, right? And so we'll make use of this. I think a program looks good. I think this is probably all we need. We'll see if we need something more. We'll add more things as needed. So now that we've passed our data, let's now then I want to create my program object, right? So let's call it parse program, right? And so my parse program will receive an array of strings, basically all the instructions, and then we should return a program object, right? And how we will do that is, we already know how to parse each instruction, right? So what we can say is, where, let's say is, which, let's say that's the instruction array, so that will simply be a map of parse instruction. Let's say this is is the input string, and then this is literally instructions. So mapping parse instruction over is gives us the list of instructions, and using this now we can create our program, right? So we'll say ACC, now that starts at 0, we know that. Now I pointer should also start at 0, and then at the end we have instructions. Oops. Right, and I think that should be it. Yeah, so this let's reload, and now we can say, and so when we say this, now it has successfully passed the program, right? Because now we see that the ACC is 0, the the instruction pointer starts at 0, and we have instructions which have already been passed, and they are just these 2 instructions. Cool. So now this allows us to actually create a program, right? From the input, what we need to do is actually figure out how to execute them, right? So for that, the first thing I'll probably start with is, let's say, execute program. And now by execute program, I think would take a program as an argument, right? And it would probably do some operation based on the instruction, and then it should return a program. Now the reason we do this is because obviously program and most other data types we have, they are immutable, right? So we don't mutate an existing thing. All we ever do is we make changes and create a new one based on that. And so let's see what this would look like. So execute program, let's say it receives a program, and now where instruction is equals to no, let's do that. Sorry. The next program would essentially just be program with ACC being, let's say, equals to the next ACC value. This would depend on the instruction somehow, and then we have the I pointer, then and that, let's say, should be equal to the next I pointer, and finally we have instructions which technically would just get copied over. And now this is already partially true, except of course now we need to figure out how to get the value of the next accumulator and the next pointer. For that, maybe I think, okay, what I probably want to do is write a separate function that knows how to execute an instruction. And now the only thing here we need is the fact that since the accumulator and the instruction pointer are essentially like a global value which is outside the outside the data that instruction holds, I think for us it'll be best if we just pass it to the execute instruction method, which will then finally, based on these values, I think return the next set of values for them. So let's use a tuple for that, right? So and what we can say now is, so we'll receive an instruction. Now let's do a pattern match for instruction. We know the instruction can be either ACC. We can with some argument, right? And let's say we have the current ACC value and the current I pointer value. If we have this, then, and since we know that we are basically executing the ACC instruction, what we need to do is increment the ACC, the existing ACC value, by the argument, and we will increment the pointer by 1 so as to say that we move to the next instruction. And similarly, let's do the jump. Oops. Now for jump, obviously the ACC doesn't change at all, but the I pointer changes by R value, right? Because we know that R could be either positive or negative. We just add it to I pointer, and that will automatically ensure that that basically tells us what should be the next statement to execute. And then finally we have the nope operation, and again in this case as well, the ACC doesn't change at all. However, we move the instruction pointer by 1, right? So the instruction pointer goes to the next statement. Right, so now given that we have this, now let's utilize this. So now in our where clause, we can say that the next accumulator and the next I pointer will essentially be, we can get that from by executing the instruction, right? Because when we execute the instruction, that's what we will get. So we need to also right. So we've also passed the ACC and the I pointer value. I think we already know how to execute the program. The only problem obviously we have is the fact that because we know there's an infinite loop, this will just keep executing it forever and it will never actually stop. So the criteria to stop, which has been specified, is the fact that as soon as we hit an instruction that we've already executed, that's what we treat as the point where we want to terminate our program. And the best way to do that is basically have a map where we keep record essentially of all the instruction pointers that we have traversed so far. And as soon as we reach an instruction pointer which has already been traversed before, we halt our program. Yeah. Okay. Now this is a little bit wordy, but and it's definitely going over the length. So maybe we will do it. I don't know if this works, but let's try it. Okay, yeah, so we can't, let's name it something else. And so we will say this, and we will say this, and we will say ACC value is ACC program. Let's use the same concept. We say so the ACC value is ACC program. I had the ITR value is ITR, sorry, IPTR IPTRB. So we will say IPTRB here. The ACC is B. This is IPTRB. Yeah, I think this reads slightly better. It's shorter. So yeah, so now what we need to do is basically let's build the execution wrapper, which will ensure that we halt when we reach the same instruction to again. Let's call it execute program, not instruction. And this should definitely receive a program. And what I'll do is to make things easy for me, we will just basically return the value of the accumulator, I guess. We could return the program also, but let's look at that. Okay, let's look at let's look at what and okay, of course the one thing we need is the fact that we need to keep track of the instructions that we have, the history of instructions that we have executed, because we need to determine whether we're coming at an instruction that we've already processed. For that, let me import the data.map.strict as m, right? We will use a map, and so m.map, and we'll basically use the I pointer as the key and the value as, let's say, a bool, and then eventually we will return a program. So to execute program till loop, we'll receive a program and a memo, right? And now if we see that if I pointer of program is a member of memo, then we know that we are executing an instruction that has been executed in the past. Okay, and if that is the case, then we will finally return the final program, which would be basically a copy of the state of the program. So ACC would be ACC of program, and IPTR would be IPTR. So technically we're not really interested in the remaining stuff. So to make things simple, let's just directly return the value itself. That way we can just say this and we'll just return the value, because that's what we ultimately want. Right, so the first clause is that okay, if it's already been processed before, we know we are reaching it for the second time, so we don't even bother processing it. All we do is return the current accumulator value. That's what we need. Now otherwise what we want to do, of course, is to execute the next program instruction till almost forever. So the next program and the next memo as well, we'll see. So now where in program obviously is just execute program of program, and in memo would basically be m dot insert ptr of program, and we'll insert true for this. Yeah, this will be the next memo. So essentially we cache, we basically mark the pointer value for the program as visited because we've processed it. Yeah, that's pretty much it, honestly, isn't it? Now what we need to obviously change is we will receive just them as strings. So for that we just say lines. Okay, and now what we will do is we will obviously we would need to create our program. Let's say where program is equals to create program from is, let's say, is the input string. So this helps us create the program. Then we would execute program till loop, give it the program and give it an empty map, because obviously we start with empty. Now let's look at what the, I think this is it. I think it's taking a while. 5. What did the thing say? It should be 5. Now I already have the input because when I solved it, I have it. Now we see that the puzzle answer should be 1548. Let's try it against the input. It should run, yeah, 1548. Yeah. So our program works. Program actually works.